Welcome everyone to Group 4 podcast. Let me introduce our guests today. First is Teo Yan An.
Hi.
Next, Seng Yao. And then Wong Wei Jian. And then our good friend Yang Zheng Jie.
Hi everyone.
And also me, Wong Wei Jian. So today we are going to talk about inside Bioreactor, which analytical method best track product use. So first, the tracking product yield inside Bioreactor is critical for optimizing bioprocess and ensuring economic viability. And it also involves real-time and also offline measurement of target products. For example, monoclonal antibiotic, vaccine, and also communicator protein. Next is the category. First, it consists of chromatography. It separates identical target product from compressed cell culture medium. Next is mass spectrometry. It provides highly sensitive and specific identification and qualification. Next is spectroscopy. It allows real-time and line monitoring of product yield. Next, why we use analytical techniques? First is used to prevent batch failure and waste. Next, we allow the engineer to find out a solution most favorable harvest time for optimizing yield. Next, it can reduce risk of the contamination and manual labor. And then next, I will invite Wong Wei Jian to explain about the principle of analytical technique.
Okay, we try. So for this topic, we are focused on two techniques, which is UV spectrophotometry and the HPLC. So first, let's look at the UV spectrophotometry. The principle here is the Beer-Lambert law. When we shine a beam of light through the bioreactor sample, the molecules, specifically those who chromophore, absorb energy. By measuring exactly how much light is lost as it passes through the sample, we can instantly calculate the concentration. Is the faster ways to get a pulse on the biomass density inside the tank. Okay, next. So for the HPLC, the principle here is the differential migrations. You can think of the HPLC column as a narrow racetrack filled with the obstacles. So we inject our fermentation broth and the different components like glucose, lactic acid, and also our target protein to interact with the obstacles differently. They separate based on their chemical affinity. By the time they reach the detector, they are no longer a mixture but a series of distinct peaks. By calculating the peak area, we achieve a level of quantitative accuracy that is the gold standard for determining final product. Yan An, can you share about the critical evaluation?
Of course, I will share about some critical evaluation. Okay, so we go for the next parts. First part is the specificity of which I can say is selectivity. For this part, we will use HPLC and UV VIS spectrometer to do a comparison. First of all, HPLC is excellent selectivity than the UV VIS, and UV VIS is a poor to moderate. This is because HPLC have the ability to separate closely related compounds based on their interaction with the stationary phase and the molecule mobile phase. But for the UV VIS is the chemical reaction might react with other similar molecules or byproducts in the groove, leading to the false overestimation of the yield. Next we will go into the this is the example. You can see when we inject the sample into the HPLC column, it will separate. Next, and this is the UV VIS. Next, for the second part, we will see the data provide. For the HPLC, it will provide multi-component, but UV VIS spectrophotometry only a single component. Let's look about the example. Next. So as you can see, the HPLC can see many elements at the same time, but the UV VIS only can see some element at the same time. Next. Okay, so now we will go to the sample preparation. HPLC have the high sample preparation, but UV VIS have the more higher sample preparation. This is because HPLC requires centrifugation to remove biomass and microfiltration to prevent destroying the expensive column. But for the UV VIS, it requires manual wet chemistry step. For example, adding reagents to become the solution. Okay, next. So these are the steps. As you can see, the UV VIS have the more steps due to the HPLC. Next. Okay, so we go to the cost and complexity. HPLC have the higher cost than the UV VIS. This is because the machine is more expensive and than the UV VIS. Next, we can look for the example. As you can see, the machine is approximate price $16,000 to $100,000, and for the maintenance fee, it spends a few $1,000s per year. Next, but for the UV VIS, it only costs $1,000 to $30,000 for the equipment. Okay, next. Okay, last we go to the analysis speed. HPLC have a slow analysis speed, but UV-VIS have the fast analysis speed. This is because HPLC will take 15 to 30 minutes per run to get all the samples, and but for the UV-VIS only take a few seconds to take one sample. Okay. So Mr. Seng Yao, can you talk us more detail about the sample preparation?
Yes, sure. So I will talk about the sample preparation. The scenario we use in monoclonal antibodies, and the bioreactor we use is the protein A affinity HPLC. We begin with the step 1, clarification and sample preparation. To protect our HPLC system, we must remove all biomass from the bioreactor sample. We draw a 2 ml sample and centrifuge at 12,000 rpm for 10 minutes to pellet the CHO cell. Then we take the clear supernatant and pass it to a 0.22 micron low protein binding filter. This ensures no microparticles enter the column and prevent the system clogging. Going to the next step, which is mobile phase preparation. The affinity mechanism relies on a 2-buffer system to manipulate the pH. Mobile phase A is our binding buffer, while mobile phase B is our elution buffer. Both buffers are filtered and degassed via sonication to prevent air bubble from disrupting our baseline. And next is step 3, column equilibration and injection. We use an analytical protein A affinity column pack with 5 micron porous speed. Before injection, we pump 100% mobile phase A through the column until the UV baseline at 280 nanometer is perfectly flat. Once equilibrate, the auto sampler inject 10 to 50 microliter of our prepared sample directly into the flow stream. This brings into the step 4, which is the HPLC gradient run, where the separation happens over 8 minutes window. In the first 2 minutes, mobile phase A wash away all host cell protein and media impurities into the waste, this creating the initial flow through peak. At minute 2.1, the system switched to 100% mobile phase B. The sudden drop to pH 2.8 protonates the binding site, breaking the electrostatic bond and releasing purified monoclonal antibody as an isolated elution peak. Finally, next we go into the next slide. Next, which is the data integration and quantification. The software will detect the purified antibody paste and integrate the area under the curve. So this allows us to track the bioreactor's product yield. Mr. Zheng Jie, can you tell us about the quantitative element?
Yeah, of course. I'll give an example, the production of yeast. The yeast is 10 liter, and then the fermentation run lasts for exactly 24 hours. The initial biomass concentration is 1.5 gram per liter, which grows to a final concentration of 6.3 gram per liter. Over the same period, the glucose concentration drops from an initial of 50 gram per liter down to a residual of 2.0 gram per liter. To determine the exact internal concentration, the final cell-free supernatant is analyzed via HPLC. The instrument is calibrated with standard solution, establishing a linear calibration factor of 500 mAu per second. And then the raw chromatogram for the 24-hour sample reveals a peak area of the 1105 kilo mAu per second. No ethanol peak was detected as our 0. So step 1 is to calculate the final ethanol concentration. And HPLC doesn't directly spit out a concentration like 22.1 gram per liter. Instead, it generates a chromatogram with peaks. And the machine measures the peak area for each substance. The HPLC peak area reading is divided by a fixed calibration factor to get the ethanol concentration. Then the step 2 is to calculate the ethanol yield. First, we determine the total substrate cost, which is a delta S, by subtracting the final residual glucose from the initial glucose concentration. We get 48.0 gram per liter. Now we divide the net product formed by the net substrate cost. Then we get the ethanol yield is 0.46 gram per gram. It means 0.46 gram of ethanol yield when 1 gram of the glucose is consumed. Then at step 3, we calculate the volumetric productivity of the ethanol, which is denoted by the QP. We divide the product concentration by the total time, which is 24 hours, and we get a value of 0.92 grams per liter per hour.
So throughout this stirring season, we found that UV-vis method is a very rapid and inexpensive compared to the other ones. The bioreactor itself is an unpredictable mixture of different chemical byproducts, and the reagents for UV-vis analysis are also known to have problems with cross-reaction, which resulting in a very high chance of getting a misleading positive yield result. So HPLC is chosen as a method since it is absolutely precious due to its highest specification. Next, this is the reference that we refer to. So that's all for us. Thank you.